Hello everyone, welcome to this lecture. I am Amlan. Today I will discuss about vector atom model, spin orbit coupling and space quantization. Okay. Bohr-Sommerfeld model is inadequate to explain several observed facts such as multiplet structure of lines of alkali spectra, anomalous Zeeman effect, etc. To explain these facts, two Dutch physicists G. E. Uhlenbeck and S. A. Goudsmit in 1925 proposed the vector atom model, which is an extension of Bohr-Sommerfeld model by incorporating into it two new ideas. First idea is an electron in an atom has a spin motion in addition to its orbital motion, that is, in classical concept, rotation about its own axis. Okay. And the second postulate is the orbital angular momentum PL and the spin angular momentum PS of an electron in an atom are quantized, both in magnitude and their relative directions. Okay. So, the total angular momentum is Pj vector equals to PL vector plus PS vector. Okay. Here PL, PS and Pj are quantized as PL equals to L into H by 2 pi, PS equals to S into H by 2 pi and Pj equals to J into H by 2 pi. Okay. Here L is orbital quantum number, S is spin quantum number and J is total angular momentum quantum number. Okay. And the value of L is L equals to 0, 1, 2, 3 to N minus 1 and value of S is S equals to half and value of J is J equals to L minus S and L plus S for L does not equals to 0 and equals to S for L equals to 0. Okay. Now here N is called principal quantum number. Okay. Now an electron in an atom moving in an orbit has a orbital magnetic dipole moment mu L vector equals to minus E by 2m into PL vector. Okay. And its magnitude is mu L equals to E by 2m and the value of PL is L into H by 2 pi. Okay. So this is equals to L into EH by 4 pi m. Now this is denoted as mu b. So this is equals to L into mu b. Okay. Where mu b equals to EH by 4 pi m. Mu b is a suitable unit for measuring magnetic dipole moment of atoms and it is called Bohr magneton. Okay. So this is called Bohr magneton. Now due to spin motion, an electron has a spin magnetic dipole moment mu s vector equals to minus E by m into ps vector. Okay, this can be written as this is equals to minus 2 into E by 2m into ps vector. Okay, and its magnitude is mu s equals to E by m, and the value of ps is s into h by 2 pi. Okay, now value of s is half, so this is equals to E by m into half into h by 2 pi. So this is equals to EH by 4 pi m. Now this is equals to mu b. Okay, that is Bohr magneton. So this is equals to mu b. Thus we get the magnitude of spin magnetic dipole moment mu s is this, and the magnitude of orbital magnetic dipole moment mu l is this. Okay, now we discuss two important things. One is spin orbit coupling and other is space quantization. Okay, so first we discuss spin orbit coupling. So first we discuss spin orbit coupling. Now, an electron in an atom moving in an orbit finds the nucleus of charge plus Ze moving around it. Now, relative to the electron, the orbital motion of the nucleus produces a current loop which produces a magnetic field, and that magnetic field interacts with the spin magnetic dipole moment mu s of the electron. Okay, and this interaction is called spin orbit coupling. Now, due to this interaction, that is spin orbit coupling, both PL and PS will precede around the direction of PJ. Okay, due to this spin orbit coupling, PL vector and PS vector, this is PL vector and PS vector will precede around the direction of PJ vector. Okay, now taking into account the relativistic variation of the mass of the electron and spin orbit coupling, the energy of the electron is given by E equals to minus mz square e to the power 4 by 32 pi square epsilon 0 square n square h cut square into 1 plus z square alpha square by n square into n by l plus half minus n by l into j plus 1 minus l into l plus 1 minus s into s plus 1 by 2 l plus half into l plus 1 minus 3 by 4. Okay. Here alpha equals to E square by 4 pi epsilon 0 ch cut, and its value is approximately 1 divided by 137. Alpha is called fine structure constant. Okay, so alpha is called fine structure constant. Now, this equation shows that energy E depends dominantly on N but varies very slightly with J and L. Okay. So the spin orbit coupling and the relativistic mass variation of the electron causes very fine splitting of the energy of the electrons. Now here transitions are followed by the selection rule delta L equals to plus minus 1 and delta J equals to 0 plus minus 1. Okay. Now with this idea, the fine structure of hydrogen spectral line has been successfully explained. Okay. Now we discuss another important thing, that is space quantization. Okay. Now we discuss space quantization. When a magnetic field of induction B is applied to an one electron atom due to the interaction of B with mu L and mu S, torques will act. Now in case B is relatively strong, okay, in case B is relatively strong, the spin orbit coupling will break down and PL vector and PS vector will precede around the direction of B, maintaining such constant angle alpha and beta with B that the normal projection of PL and PS on the direction of B is quantized as PLB equals to PL cos alpha equals to ML into H cut, where ML equals to 0 plus minus 1 plus minus 2 dot dot plus minus L. Okay. And PSB equals to PS cos beta. This is equals to MS into H cut, where MS equals to plus minus half. Okay. Here ML is called orbital magnetic quantum number and MS is called spin magnetic quantum number. Okay. Now we draw PL vector and PS vector and the angle that makes with B vector. Okay. Suppose magnetic field acts in this direction. Okay, so this is B vector. Now suppose this is PL vector. Now we know that mu L vector has same magnitude but opposite direction as that of PL vector. Okay, so this is mu L vector, and the angle between PL vector and B vector is alpha, so this angle is alpha. Now in this case, when B is relatively strong, the spin orbit coupling will break down and PL will precede around the direction of B. Okay, maintaining constant angle alpha. Okay, PL will precede around the direction of B, maintaining constant angle alpha, and the projection of PL on the direction of B is quantized, that is ML into H cut. So this is ML into H cut. Okay, this is ML into H cut. Now suppose this is magnetic field B and this is PS vector and this is mu s vector. Okay, and the angle between PS vector and B vector is beta, so this angle is beta. Now here also, in case B is relatively strong, then spin orbit coupling will break down and PS vector also will precede around the direction of B. Okay, PS vector also precedes around the direction of B, maintaining constant angle beta with B. Okay, so here the projection of PS on the direction of B is quantized, that is ms into h cut is quantized. So this is ms into h cut. Okay, now as a result, additional term will be introduced in the energy of the electron given by delta EL equals to minus mu L dot P and delta ES equals to minus mu S dot B. Okay. Now this is for the case when B is relatively strong. Now suppose in case B is weak. Okay, in case B is weak, the spin orbit coupling will persist and PL and PS will add vectorically to give PJ vector, which will precede around the direction of B, maintaining such constant angle gamma with B that the normal projection of PJ on the direction of B is quantized as PJB equals to PJ cos gamma, and this is equals to MJ into H cut, where MJ equals to, MJ has value minus J to plus J in equal steps of unity, that is MJ equals to minus J minus J minus 1 minus J minus 2 to J minus 1 and J. Okay. Now suppose magnetic induction acts in this direction, so this is B vector, and suppose this is PJ vector and this is mu J vector. Okay, and the angle between PJ and B is gamma, so this angle is gamma. Now in this case when B is relatively weak, okay, B is weak, then PJ will precede around the direction of B, maintaining constant angle gamma with P. Okay, so here this is MJ into H cut. Okay, this is MJ into H cut, and this is quantized. That is, the projection of PJ on the direction of B is MJ into H cut is quantized. And here in this case, additional energy will be delta E equals to minus mu J dot B. Okay. Now, in an atom containing more than one electrons, the total angular momentum measured in the unit of H cut is denoted by J vector. Okay, so this is the total angular momentum of the atom, and it is obtained by two different ways. total angular momentum J is obtained by two different ways. First way to find total angular momentum of the atom J is the orbital angular momenta of different electrons are added to produce total orbital angular momentum of the atom, that is summation over I Li equals to L. Okay, so Li is the orbital angular momentum of each electron, and capital L vector is the orbital angular momentum of the total orbital angular momentum of the atom. Okay, and the orbital spin angular momentum of different electrons are added to produce total spin angular momentum of the atom, that is summation over I Si equals to S vector. Okay, so Si is the spin angular momentum of each electron, and capital S vector is the total spin angular momentum of the atom. Now L vector and S vector add vectorically to give total angular momentum J vector of the atom, and this process of addition is known as LS coupling. Okay, so this is called LS coupling or Russell-Saunders coupling, and it holds for atoms of low atomic number. Okay, so it holds for atoms of low atomic number. Now the second process to find J is the orbital angular momentum and the spin angular momentum of each electron are added to produce total angular momentum of the electron, that is for ith electron Li plus Si equals to Ji. Okay, so this is the total angular momentum of the ith electron. Then the total angular momentum of each electron are added to produce total angular momentum of the atom, that is summation over I Li equals to summation over I Ji equals to J vector. Okay, first we are doing that the orbital angular momentum and the spin angular momentum of each electron are added to produce total angular momentum of the electron. Okay, then the total angular momentum of all the electrons are added to produce total angular momentum of the atom. Okay, and this process of addition is known as JJ coupling. Okay, so this is called JJ coupling, and it holds for atoms of high atomic number. Okay, so it holds for atom of high atomic number. Okay, so this is LS coupling and this is JJ coupling. It holds for atoms of low atomic number and it holds for atoms of high atomic number. Okay. Now the addition of Li are quantized. Okay. The addition of Li are quantized. For example, for a 2 electron atom, with L1 equals to 2 and L2 equals to 1. Okay. For a 2 electron atom with L1 equals to 2 and L2 equals to 1, L vector, capital L vector that is sum of L1 and L2 has three values. Okay. L has three values, that is L1 plus L2 to L1 minus L2 in equal steps of unity. So here for 2 electron atom with L1 equals to 2 and L2 equals to 1, L has three values. One value is 3, 2 and 1. Okay. Suppose this is L1 equals to 2 and this is L2 equals to 1. Okay. So the addition of L1 and L2 is capital L. So this is L. Since both are parallel, so L is 2 plus 1 equals to 3. So one value of L is 3. Now suppose this is L1 and this is L2. So addition of capital L is here, L equals to 2. Okay. Now another possibility is, suppose this is L1 equals to 2 and this is L2 equals to 1. So the resultant L is L equals to 2 minus 1, that is 1. Okay. So for a 2 electron atom with L1 equals to 2 and L2 equals to 1, L has three values. One value of L is 3, the second is 2 and other value of L is 1. Okay. So these are the addition of Li are quantized. Now in the addition of Si, they are either parallel or anti-parallel, such that in case of odd number of electrons, S is half integral, and in case of even number of electrons, S is either 0 or positive integer. Okay. So in case of odd number of electrons, S is half integral. And in case of even number of electron, S is 0 or positive integer. Half integer. Okay, that is in case of odd number of electron, S is half integer, and in case of even number of electron, total spin quantum number S is either 0 or any positive integer. For example, for a 3 electron atom, suppose this is S1 equals to half, this is S2 equals to half, and this is S3 equals to half. So the total S is capital. Here all are parallel. Okay, all are the same direction. So total S is S equals to half plus half plus half, that is 3/2. Okay. Now another possibility to find S is, suppose this is S1 equals to half and this is S2 equals to half. Okay, and this is S3 equals to half. So here S1 and S2 are parallel, but S3 is anti-parallel. So the addition of all Si are, S is half plus half minus half, that is half. Okay, so this is S vector, this is S. Okay, total S. So for a 3 electron atom, S equals to 3/2 and S equals to half. Okay, that is for odd number of electron, S is half integer. Okay. Now we discuss for 4 electron atom. Okay. for a 4 electron atom, suppose this is S1 equals to half, this is S2 equals to half, this is S3 equals to half, and this is S4 equals to half. Okay. Now all are in parallel. Okay. So the addition of SIR, S equals to half plus half plus half plus half, that is 2. So one value of S is 2. Now another possibility is, suppose this is S1 equals to half, this is S2 equals to half, this is S3 equals to half, and this is S4 equals to half. So here S1, S2 and S3 are parallel, but S4 is anti-parallel. So the addition of S is S equals to half plus half plus half minus half, that is 1. Okay. Now third possibility is, suppose this is S1 equals to half and this is S2 equals to half, and this is S3 equals to half, and this is S4 equals to half. So here resultant S is S equals to half plus half minus half minus half, that is 0. Okay. So for a 4 electron atom, S equals to, one value is 2, S equals to 1 and S equals to 0. Thus for odd even number of electron, S is 0 or positive integer. Okay. And in case of odd number of electron, S is half integer. Okay. Thus we discuss vector atom model, spin orbit coupling and space quantization. Okay. Thank you for watching this video.